An invisible river flows through the universe right now, passing through every object and even your own body. This silent, ghostly downpour is made of neutrinos, the most elusive particles in existence. While you read this, trillions of these cosmic messengers are streaming through you every second, completely unseen and unfelt. What are these ghost particles, and what profound secrets about the universe's most violent explosions and its very first moments are they whispering to us? By the end of this journey, you will understand how catching these phantoms is rewriting the laws of physics. We will travel from their desperate theoretical birth to the monumental detectors buried deep in ice and underground, built to snare a single one. How does it change your perception of reality to know you are constantly immersed in an ocean from the dawn of time? The very existence of the neutrino was born from a scientist's quiet desperation. In the closing days of 1930, Wolfgang Pauli found himself deeply troubled by a fundamental problem. Certain types of radioactive decay seemed to be breaking one of physics' most sacred laws, the conservation of energy. The math simply did not add up, with energy mysteriously vanishing from the equations. To resolve this crisis, Pauli proposed a radical and almost embarrassing solution, a theoretical ghost. He suggested an unseen, neutral particle was carrying the missing energy away, a particle so fantastically small and non-interactive he believed it might never be observed. He confessed to a colleague in a letter, writing, "I have done a terrible thing. I have postulated a particle that cannot be detected. This was not a triumphant discovery, but a last-ditch effort to save a foundational principle of reality itself." It was a particle conceived out of pure mathematical necessity, a placeholder for a cosmic secret. A few years later, Enrico Fermi gave this hypothetical spectre its permanent name, the neutrino, meaning little neutral one in Italian. The initial reaction from the wider physics community was steeped in skepticism. How could you prove the existence of something designed to be invisible, a phantom invented merely to balance an equation? This profound mystery of a particle that should not be detectable yet had to exist launched a decades-long quest that would push the very limits of human ingenuity. Deep within the sun's core, a continuous cosmic firestorm rages. Under unimaginable pressure and temperatures of millions of degrees, the very building blocks of matter are forced together. Hydrogen nuclei fuse into helium in a frantic dance known as the proton-proton chain reaction. This is the primary engine of our star, and with every single fusion event, alongside a flash of energy, a neutrino is born. This means our sun is not just a source of light and heat, it is a relentless neutrino factory operating at a scale that defies comprehension. Every second, approximately 100 billion of these solar-born neutrinos pass through a space as small as your thumbnail. This staggering number highlights their ghostly nature, for you feel nothing, see nothing of this constant subatomic rain. Their journey from the sun to you is a testament to their strangeness. A photon of light created in that same solar core bounces around for tens of thousands of years before finally escaping the sun's dense interior to travel to Earth in just over 8 minutes. But a neutrino, interacting with almost nothing, escapes the sun's heart in barely 2 seconds. This incredible speed and directness makes them something truly special, a live broadcast from the very center of our star. They are the only direct messengers we have from the sun's powerful engine, offering a pure, unaltered signal of what is happening right now, a million years before the light from those same reactions even begins its long journey outward. But a star's steady neutrino heartbeat is only the beginning. The true power of these ghost particles is revealed in stellar death. Picture a massive star, many times larger than our Sun, finally exhausting the nuclear fuel in its core. For millions of years, the outward push of fusion fought a delicate battle against the star's own immense gravity. Now that fight is over. In less than a second, the core collapses, crumpling under a weight it can no longer support. This is a supernova, one of the most violent events in the cosmos. And in that final, catastrophic implosion, something astonishing happens. While the outer layers of the star are blasted outward in a brilliant flash of light, the true energy release is happening invisibly. 99% of the supernova's titanic energy is not carried by light, but is instead radiated away in a single, stupendous burst of neutrinos. For about 10 seconds, this single dying star unleashes more neutrinos than the combined output of every star that has ever shone in the observable universe. It is a fleeting, unimaginable pulse, a ghostly scream announcing a stellar death. This was not just a theoretical idea. In February of 1987, for the first and only time in history, detectors on Earth recorded a handful of these cosmic messengers from a supernova in a neighboring galaxy, the Large Magellanic Cloud. That event, Supernova 1987A, marked the true birth of neutrino astronomy. Those 24 detected neutrinos, arriving hours before the visible light reached our telescopes, confirmed the fundamental models of how stars die. They were the direct signal from the collapsing core itself, a message from the heart of the explosion. This single observation opened an entirely new window on the universe's most extreme phenomena, proving that neutrinos could be our eyes where light fails. It forces us to ask, if a dying star can produce such a flood, what other, even more profound secrets are these silent messengers carrying from the darkest and most energetic corners of reality? Yet the death of a single star is just one source in a far more energetic symphony. Across the cosmos, particles are being accelerated to velocities approaching the speed of light. These are cosmic rays, primarily single protons, that race through the void. Their origins are some of the universe's most violent environments, from the swirling disks of matter around supermassive black holes in active galaxies to the colossal explosions of gamma-ray bursts. But these protons are not silent travelers. On their immense journeys, they inevitably collide with other particles or even the thin gas that drifts between the stars. The result is a spectacularly violent event, a cosmic car crash of unimaginable scale. From the chaotic aftermath of these collisions, a cascade of secondary particles erupts. And amidst this subatomic shrapnel, new neutrinos are born. These are not the gentle, steady stream from our Sun. These are high-energy neutrinos forged in the heart of cosmic violence. While their solar cousins tell us about stellar furnaces, these carry a far more extreme message. They are direct, unimpeded tracers of the universe's most powerful particle accelerators. Unlike the protons that created them, which are bent and redirected by interstellar magnetic fields, neutrinos travel in perfectly straight lines, completely unaffected by these cosmic magnets. This gives them a unique and powerful property. By detecting one of these high-energy ghosts and tracing its path back across the universe, we can point directly to its source, to the specific cataclysm that hurled it into the void. This potential turns the neutrino from a mere messenger into a perfect cosmic arrow, one that could lead us directly to the engines of the most energetic events since the Big Bang. At the very bottom of our world, a silent sentinel waits in a landscape of breathtaking desolation. The Amundsen-Scott South Pole Station rests upon an ice sheet miles thick, a place where the air is so cold and dry it feels like another planet. And deep within this ancient, perfectly clear ice, scientists have engineered one of the most ambitious experiments ever conceived, the Ice Cube Neutrino Observatory. This is not a traditional telescope of glass and metal pointing at the sky. It is a trillion-ton detector, a cubic kilometer of the Antarctic ice cap itself, transformed into a colossal hunting ground for cosmic ghosts. Buried more than a mile beneath the surface are over 5,000 ultra-sensitive digital optical modules, strung on cables like pearls on deep-sea fishing lines, frozen solid into the absolute darkness. This entire frozen volume is the instrument, a silent witness to the universe's faintest whispers. The principle of its operation hinges on a rare moment of interaction. When a single high-energy neutrino, after traveling across the cosmos for millions of years, finally and miraculously collides with the nucleus of an atom in this deep ice, the collision creates a secondary particle known as a muon. This muon, born from the ghost's fleeting touch, travels faster than light can move through the dense, frozen medium. And just as a supersonic jet creates a sonic boom, this faster-than-light particle generates a shockwave of pure blue light called Cherenkov radiation. It is this faint, ethereal blue flash that the frozen sensors capture. By precisely timing the arrival of this ghostly light at different sensors, scientists can perform a kind of subatomic triangulation, reconstructing the neutrino's incoming path with stunning accuracy and measuring its immense energy. The monumental scale of this effort, drilling 86 holes into the polar ice to lower these sensors into the eternal deep freeze, underscores a profound truth about our quest for knowledge. We must build instruments of almost unimaginable scale and ingenuity just to catch the faintest echo of the universe's grandest events. Each precious blue flash is a message in a bottle, cast adrift from a cosmic cataclysm, and its detection here at the bottom of the world marks a triumph of human curiosity. Even the ghost, it turns out, has more than one face. For decades, scientists thought of the neutrino as a single type of particle, but a startling discovery revealed they are not a single entity. They exist in three distinct identities, whimsically named flavors. There is the electron neutrino, the muon neutrino, and the tau neutrino, each one a partner to its respective charged particle in the subatomic family. This simple classification, however, soon led to a profound cosmic puzzle. When physicists first built detectors to catch the neutrinos streaming from the sun, they were met with baffling results. Their intricate instruments, designed to spot electron neutrinos from the solar furnace, registered only about 1/3 of the predicted number. The rest had simply vanished. It was as if a river was flowing from a known source, yet by the time it reached you, 2/3 of its water had inexplicably disappeared. Where did the missing neutrinos go? The answer was more bizarre than anyone had imagined. The neutrinos were not missing at all. They were merely in disguise. On their long journey from the sun's core to our detectors on Earth, these particles were performing a spontaneous quantum metamorphosis. An electron neutrino born in a fusion reaction could transform into a muon neutrino, and then perhaps into a tau neutrino before changing back again. This chameleon-like behavior is known as neutrino oscillation. The sheer act of changing flavor as they travel through empty space revealed a secret that overturned a fundamental pillar of physics. For oscillation to be possible, neutrinos must have mass. This was a monumental shock to the scientific community. The long-established standard model of particle physics, our most complete theory of the fundamental forces, had always assumed neutrinos were massless, just like the photon. The discovery of their tiny but non-zero mass meant the rulebook needed a major rewrite. These phantoms, once thought to be simple cosmic messengers, were in fact holding keys to a deeper reality, pointing toward physics that lies far beyond our current understanding of the universe. This profound mystery of the neutrinos' mass points toward an even deeper cosmic puzzle, one that questions our very existence. The universe we observe is made almost entirely of matter. Every star, every planet, and everything on it is built from it. Yet our most fundamental theories tell us the Big Bang should have created equal amounts of matter and its mirror opposite, antimatter. When a particle of matter meets its antimatter twin, they annihilate each other in a flash of pure energy. So if the early universe had a perfect balance of both, all of it should have simply vanished, leaving behind an empty, featureless cosmos. The fact that we are here at all means something must have tipped the scales. A tiny 1 in a billion asymmetry must have favored matter, allowing a remnant to survive the great annihilation and form everything we see. But what physical process could have broken this perfect symmetry? The answer might lie within our ghostly neutrino. Physicists have observed a subtle effect known as CP violation, where particles and antiparticles behave in slightly different ways. This asymmetry is a required ingredient for creating a matter-dominated universe, but the amount we have seen in other particles is far too small to account for the world we live in. Neutrinos, however, could be the key. There is a compelling theory that suggests neutrinos are their own antiparticles, a unique class of entity known as Majorana particles. If this is true, then in the searing heat of the early universe, these special neutrinos could have decayed in a way that inherently favored matter over antimatter through a process called leptogenesis. This would mean the neutrino's unique quantum properties didn't just give it mass, they may have actively sculpted the cosmos. The hunt for proof is now underway in laboratories deep underground, where scientists are searching for an incredibly rare nuclear event called Neutrinoless double beta decay. Observing this process would confirm that the neutrino is its own antiparticle, providing the missing link in the story. The same phantom that passes through us unseen could be the very reason any of us are here to notice it at all. The sheer smallness of neutrino mass is a puzzle that defies all common sense. An electron has mass, but a neutrino is millions of times lighter, a mere whisper of substance. This incredible lightness places these phantoms in a category all their own, forcing physicists to question how such a tiny amount of substance can even exist. The very framework that gives other particles their heft, the famous Higgs field, seems insufficient to explain a mass so vanishingly small. It suggests that an entirely different, hidden mechanism might be at work, one that operates on scales and principles we have yet to fully grasp. This leads to one of the most profound questions in modern physics. Is the neutrino a Dirac particle like the electron with a distinct antimatter twin? Or is it something far more exotic, a Majorana particle where the neutrino and antineutrino are one and the same, a true ghost that is its own mirror image? The answer is not just academic trivia. If the neutrino is its own antiparticle, it would mean that these particles could effectively annihilate themselves in a unique quantum process, a property that could have been the cosmic trigger that filled the universe with matter. This fundamental property is inextricably linked to the ongoing hunt for their absolute mass. Laboratories across the globe are running painstaking experiments, not to catch neutrinos from space, but to meticulously weigh them. They study the subtle endpoint of energy spectra in radioactive decays like tritium, searching for the almost imperceptible imprint that a neutrino's minuscule mass leaves behind. Every new, tighter limit on that mass scale challenges our theories further. How can something so fundamental to the cosmos be so elusive, so barely there? This bizarre, minimal nature pushes us to consider possibilities that sound like science fiction, from extra dimensions of space to new, unseen symmetries of nature. The neutrino, it seems, is not just a messenger from the stars, but a guide pointing toward the deepest and most mysterious layers of quantum reality. But the story of the neutrino begins long before the first star ever ignited. We must travel back to the universe's first second of existence, to a moment of almost incomprehensible density and heat. In this primordial fireball, the entire cosmos was a seething, opaque soup of fundamental particles. Light itself, in the form of photons, was trapped, constantly bouncing off a thick fog of electrons and atomic nuclei, unable to travel freely. Yet, just 1 second after the Big Bang, as the universe expanded and cooled to a critical point, a profound transition occurred for our ghostly particles. Neutrinos, which had been constantly interacting with this dense plasma, suddenly found themselves liberated. Their incredibly weak interactions meant that as the universe thinned out, they simply stopped colliding with other matter. They decoupled and began streaming unimpeded through the expanding cosmos. This event created the very first fossil field, a relic sea of neutrinos that has been flowing through the universe ever since. This is the cosmic neutrino background. You are immersed in it right now. For every cubic centimeter of space around you, there are roughly 336 of these ancient neutrinos. That is more than 1 billion of them for every single proton in the universe. We are all swimming in an ocean of ghosts from the dawn of time. You might be familiar with its more famous cousin, the cosmic microwave background, the afterglow of the Big Bang that we can detect as a faint radio static filling the sky. That light was freed much later, hundreds of thousands of years after the Big Bang. The cosmic neutrino background is a far older snapshot, capturing the infant universe at an age of barely 1 second. Yet detecting this most ancient of all cosmic signals remains a monumental and so far unmet challenge. These primordial neutrinos have been stretched and cooled by the expansion of the universe for over 13 billion years. They now possess unimaginably low energy, making them billions of times fainter and more difficult to catch than even the solar neutrinos we already struggle to detect. To observe them directly would require a technology far beyond our current capabilities, a detector of almost mythical sensitivity. But the mere knowledge that this background exists, this ultimate fossil, is a staggering thought. It means that with every breath, you are inhaling the echoes of creation itself. Every atom in your body is constantly being passed through by messengers from the universe's very first moment, a silent, living connection to the origin of everything. This profound weakness, this ghostly ability to pass through entire planets, stems from one of the universe's 4 fundamental forces. Neutrinos are subjects of the weak nuclear force, the most introverted and short-ranged of all nature's interactions. It only operates at subatomic distances, 1,000,000 times smaller than the width of a single atom. To grasp why this makes them so elusive, picture an object of human scale, like a vast, empty sports stadium. Now imagine you're standing at one end and you throw a single baseball toward the other side. Somewhere in that immense open space, there is one single tiny pebble. The chance of your baseball striking that one specific pebble on its journey across the stadium is almost zero. This is the reality for a neutrino passing through your body. The atoms that make up your flesh are mostly empty space, with their tiny, dense nuclei acting as those isolated pebbles. A neutrino only notices a nucleus if it can get phenomenally close, well within the minuscule range of the weak force. Otherwise, it simply sails through the vast emptiness of the atom, completely unaffected by the electromagnetic forces that govern our everyday world. This leads to a statistic that bends the mind. For a typical neutrino, the odds of it interacting with any matter are so incredibly small that it would likely have to travel through a solid wall of lead stretching for an entire light year. a distance of over 9 trillion kilometers, before having a 50-50 chance of finally being stopped. This is not a flaw in their design, but the very source of their cosmic power. Their profound reluctance to interact is what makes them perfect messengers. Light can be blocked, scattered, or absorbed by cosmic dust. Charged particles are sent spiraling off course by magnetic fields, but a neutrino, born in the heart of a cataclysm, flies in a perfectly straight, unwavering line, carrying its story across billions of light years completely unaltered. It is the universe's most faithful courier, a whisper that never fades precisely because it speaks to almost nothing at all. This monumental challenge of detection forces us to rely on the laws of probability itself. Since any single neutrino is overwhelmingly likely to pass through any substance untouched, the only solution is to build a target of staggering size and then wait. We must create a stage so vast and observe it so patiently that even an event with odds of 1 in a trillion becomes a matter of when, not if. The entire principle of neutrino astronomy is built on this scale, turning a question of fundamental physics into one of sheer engineering audacity. When that one incredibly rare interaction does occur, it leaves behind one of two distinct ghostly signatures for us to find. The first is the ethereal blue glow of Cherenkov radiation, the light of a sonic boom in a medium. This is the method used by colossal detectors like Super Kamiok and in Japan and IceCube at the South Pole. They use thousands of tons of ultra-pure water or deep, pristine ice as their detection medium. When a neutrino finally strikes an atomic nucleus, the collision can create a charged particle, like an electron or a muon. If this new particle travels faster than light can move through that water or ice, it generates a faint, conical burst of blue Cherenkov light. An array of sensitive photomultiplier tubes lining the detector's walls captures this fleeting shimmer, allowing scientists to reconstruct the particle's path and energy with astonishing precision. The second signature comes from a different kind of detector, one filled with a special liquid known as a scintillator. In experiments like CamLand and the upcoming Juno, the detector is a vast sphere filled with this ultra-pure liquid. When a neutrino interacts with a nucleus in this medium, the collision does not produce a faster-than-light particle. Instead, it causes the surrounding liquid to flash or scintillate with a faint pulse of light. This light is immediately picked up by an immense number of sensors, painting a detailed picture of the interaction's location and energy. Both methods, despite their different mechanisms, share one non-negotiable requirement: an almost unimaginable volume of detection material. To have any hope of catching a handful of these cosmic phantoms per day, scientists must employ thousands, even millions, of tons of water, ice, or scintillator. This is not a matter of building a bigger beaker. It is about creating an artificial planetoid of perfect purity deep underground, shielded from the constant rain of cosmic rays that would otherwise drown out the signal. This monumental effort to bear witness to the nearly invisible stands as a testament to human ingenuity, a quiet agreement with the cosmos that if we build a large enough window and wait long enough, the universe's quietest whispers will finally be heard. Deep underground in a South Dakota gold mine, a chemist named Ray Davis was attempting the impossible. His detector was a colossal tank filled with 615 tons of a common industrial cleaning fluid, perched at the bottom of the Homestake mine over a mile beneath the surface. His goal was audacious: to catch ghosts from the sun. Davis was hunting for solar neutrinos through an incredibly rare interaction, one that would transform a single chlorine atom in that vast tank into a single atom of radioactive argon. For decades, he patiently collected his data, extracting and counting these few precious atoms of argon. The results, however, created a profound crisis. His experiment was only catching about 1/3 of the electron neutrinos that solar models predicted should be arriving from the Sun. This was the birth of the solar neutrino problem, a mystery that would haunt physics for 30 years. The implications were deeply unsettling. Was our understanding of the Sun's inner furnace fundamentally wrong? Or was our grasp of the subatomic world, the very nature of these ghostly particles, completely incomplete? A quiet tension grew between astrophysicists who were confident in their stellar models and particle physicists who trusted the established rules of their field. Each side believed the other must be in error. This was not a simple experimental mistake. It was a fundamental rift in our comprehension of reality. That persistent, frustrating discrepancy, however, was the most important clue of all. The missing neutrinos were not missing. They were simply changing their identity on the long journey from the solar core. The Homestake experiment was only designed to detect electron neutrinos, and as these particles oscillated into muon and tau neutrinos during their travel, they became invisible to Davis's tank. His perceived failure was in fact a monumental success, the first indirect evidence for neutrino oscillations. The resolution of this decades-long puzzle did not just confirm our solar models, it forced a revolution in particle physics, proving that neutrinos must have mass. This story stands as a powerful reminder that in science, an anomaly is not a dead end. It is a signpost pointing toward a deeper and more wondrous truth waiting to be uncovered. Our own planet's atmosphere serves as a constant secondary source of these phantoms. High above, where the air grows thin, a relentless bombardment of cosmic rays from deep space collides with the nuclei of atmospheric atoms. Each of these violent impacts shatters the nucleus and triggers a cascade, a shower of secondary particles raining down toward the surface. And in this chaotic downpour, new neutrinos are born, specifically muon neutrinos and their counterparts. This creates a uniform, all-around rain of atmospheric neutrinos, pouring down upon the entire Earth from every direction. It was this steady, predictable drizzle that would provide the next critical clue. Deep inside a mine in Japan, the Super Kamiok and Detector, a colossal tank filled with 50,000 tons of ultra-pure water, was watching this atmospheric rain with immense precision. Its thousands of sensitive light sensors could track the faint blue Cherenkov rings created by these neutrinos, and more importantly, they could tell exactly which direction each neutrino had come from. The results were startling. The detector saw a clear and puzzling imbalance. It recorded roughly the expected number of muon neutrinos coming straight down from the atmosphere directly above. But when it looked in the opposite direction at the neutrinos that had traveled up through the entire planet to reach the detector from below, it found far fewer. This up-down asymmetry was the smoking gun. The explanation was elegant and profound. Neutrinos coming from above had only a short journey through a small amount of the atmosphere. But those arriving from below had traveled a much longer path, thousands of kilometers through the dense body of the Earth itself. That extra distance gave them more time to do something extraordinary, to oscillate, to change their identity from muon neutrinos into another flavor, tau neutrinos, which the detector at that time could not see. The ones coming up through the Earth had simply disguised themselves on the longer trip. This observation did more than just confirm oscillation. It proved this quantum metamorphosis was not a special property of solar neutrinos alone. It was a universal and fundamental behavior of the neutrino itself, a constant, shimmering identity shift happening all around us, verified by ghosts born in our own sky. While cosmic neutrinos arrive as random messengers from the depths of space, we have also learned to create our own. At laboratories like Fermilab and CERN, scientists orchestrate the birth of neutrinos with pinpoint precision. They use particle accelerators, machines that hurl protons at nearly the speed of light before smashing them into a solid target. The resulting explosion of subatomic debris is rich with unstable particles, which then decay as they travel down a long, evacuated tunnel. And in that chain of decay, a pure, intensely focused beam of neutrinos is born. This is not a gentle cosmic rain. It is a fire hose of ghosts aimed with incredible accuracy. The most audacious part of these experiments is the journey we force upon them. We shoot these man-made beams directly through the crust of the Earth, aiming for distant, massive detectors located hundreds of miles away. The planet itself becomes part of the apparatus, a filter that blocks virtually all other particles while allowing the elusive neutrinos to pass through unimpeded. This entire setup, known as a long baseline experiment, is designed to solve one of the most intricate puzzles in physics, the precise mechanics of neutrino oscillation. Because we know the exact moment the neutrinos are created, their exact flavor composition at birth, and the precise distance they must travel, we can turn their journey into a controlled laboratory. When the beam arrives at the far detector, scientists meticulously count how many of each neutrino flavor remain. By comparing the starting point to the finishing line, they can measure exactly how these phantoms morph from one identity to another over a known distance. This level of control is something cosmic sources can never offer. A supernova neutrino arrives as a singular, unpredictable event, its history and travel path largely unknown. But with an accelerator beam, every variable is measured and managed. This allows researchers to probe the subtle details of neutrino mixing with surgical precision, measuring the tiny mass differences and mixing angles that define their quantum waltz. It is a testament to human ingenuity that we can not only observe these cosmic phantoms but also summon them, bending their mysterious nature to our will in a quest to read the fine print of the universe's laws. The next leap in our quest to understand these cosmic phantoms is already taking shape in colossal laboratories buried deep beneath the Earth. One monumental project, the Deep Underground Neutrino Experiment, or DUNE, will orchestrate the most precise long-distance ghost communication ever attempted. It will generate an intense beam of neutrinos at Fermilab in Illinois and fire it straight through 800 miles of solid rock, aiming for a waiting sentinel in South Dakota. There, a mile underground in the former Homestake mine, a detector filled with 70,000 tons of ultra-pure liquid argon will stand ready to capture the arriving particles. Liquid argon is a technological marvel for this purpose. When a neutrino interacts with an argon nucleus, it creates a spray of charged particles, and in the argon, these leave behind tiny trails of electrons. By reading these electronic signatures with exquisite precision, scientists can reconstruct the interaction in stunning, three-dimensional detail, almost like watching a subatomic movie. This incredible resolution is key to unlocking one of the neutrino's most guarded secrets. Meanwhile, across the Pacific, another giant is being born. Hyper-Kamioka, under construction in Japan, is a staggering upgrade to its predecessor. Its central detector will be a cavernous tank holding 260,000 tons of the purest water, watched over by an army of sensitive light sensors. This volume is more than 5 times larger than the already immense Super-Kamioka, and the sheer scale of these two facilities, one relying on the clarity of liquid argon and the other on the vast volume of pure water, highlights the multifaceted approach needed to corner the elusive neutrino. Their scientific goals are as grand as their physical footprints. Together, they will launch a coordinated assault on the remaining mysteries. A primary target is determining the final, precise ordering of the neutrino masses. We know the three flavors have different masses, but we do not know which is the heaviest and which is the lightest. This hierarchy is a fundamental property, and knowing it is essential for understanding how the neutrino fits into the larger framework of particle physics. Perhaps the most profound quest is the hunt for CP violation in the neutrino sector. Dune and Hyper-K will analyze their beams and cosmic neutrinos with unmatched precision, searching for any subtle difference in the way neutrinos oscillate compared to antineutrinos. Finding a significant asymmetry here would be a monumental discovery, providing a compelling explanation for the matter-antimatter imbalance that allowed our universe to form. It would mean that the neutrino's quantum behavior actively sculpted the cosmos into a place where stars, planets, and life could eventually arise. Beyond these controlled experiments, these observatories will also serve as the most sensitive ears ever built, listening for the ghostly scream of a dying star. Should a supernova occur in our own Milky Way galaxy, the data from Dune and Hyper-K would be transformative. They would not just count the neutrinos, they would capture the entire energy spectrum and the precise timing of the burst, painting a millisecond by millisecond portrait of a stellar core's catastrophic collapse. These projects represent more than just experiments. They are the vanguard of a new era, designed to finally translate the silent whispers of the universe into a language we can fully understand. The most intense source of neutrinos on Earth is not a scientific instrument, but a machine built for power. Deep within a nuclear reactor's core, the controlled splitting of heavy atoms unleashes a firestorm of nuclear fission. As the resulting fragments rapidly decay, they release a staggering torrent of particles, and among them is an overwhelming flood of electron antineutrinos. A single standard power reactor can produce over 10 sextillion of these antineutrinos every single second, a number so vast it dwarfs the output of all but the most cataclysmic cosmic events. This makes the humble power plant, operating in nations across the globe, the most powerful and reliable neutrino factory humanity has ever created. For physicists, this presented an incredible opportunity. Why journey to the bottom of the world or deep underground to find a handful of cosmic phantoms when a prolific source was humming away right here? For decades, scientists have placed remarkably compact detectors, some no larger than a small car, just a short distance from reactor cores. Shielded from other radiation by thick layers of metal and concrete, these instruments do one thing exquisitely well. They count the steady pulse of antineutrinos streaming relentlessly from the heart of the fission process. This close proximity to such a pure, intense source allowed for some of the most precise measurements of neutrino oscillation ever recorded, solidifying our understanding of how these particles change their identity over even short distances. But this pure scientific inquiry has yielded an unexpected and powerful real-world application, one that touches on global security. The antineutrino flux coming from a reactor is an unavoidable physical signature, a direct and immediate readout of the reactor's power level and the precise composition of the nuclear fuel burning within its core. It is a signal that cannot be faked, switched off, or hidden behind concrete walls. The ghostly particles pass straight through every barrier. This has led to the development of reactor neutrino monitoring for nuclear non-proliferation. By placing a detector outside a reactor facility, international agencies could, in principle, remotely and independently verify that a nation's nuclear power program is operating as declared and not being used to produce material for other purposes. The same phantoms that whisper the secrets of dying stars are now being enlisted as silent, incorruptible sentinels, bridging the profound gap between the most esoteric questions of particle physics and the urgent, practical needs of our world. But the most profound source of neutrinos is perhaps the one we are standing on. Our own planet possesses a radioactive heart, and its slow, deep decay sings a ghostly song. Distributed throughout Earth's crust and mantle, vast reservoirs of radioactive elements like uranium and thorium are in a constant state of transformation. With every atomic nucleus that decays, it releases a tiny amount of heat and, in many cases, an electron antineutrino. This creates a faint, perpetual whisper rising from the ground itself, a particle known as a geoneutrino. While this terrestrial flux is utterly dwarfed by the solar downpour, it carries a message that is uniquely our own, a direct signal from the engine that drives our world's internal heat. This is not a message from distant stars, but a vital sign from the ground beneath our feet. For the first time, we have a way to listen to the planet's own slow, radioactive heartbeat. The challenge, of course, is separating this faint whisper from the immense background noise of other neutrinos. It requires the same massive, shielded detectors built for other cosmic quests. By carefully analyzing the data from observatories like CAM-LAND in Japan and Borexino in Italy, scientists can identify the specific energy signature of these geoneutrinos. Each one detected is a direct sample of the radioactive elements burning deep within the Earth, a piece of data that has traveled straight up from the mantle, completely unaffected by the hundreds of miles of solid rock it passed through. This gives geoneutrinos a power that no other tool possesses. They provide the only direct measurement of the radioactive fuel that powers continental drift, volcanoes, and the entire geothermal dynamics of our planet. For decades, geophysicists have relied on indirect models to estimate how much of Earth's internal heat comes from this radioactive decay versus primordial heat left over from planetary formation. The measurement of geoneutrinos is now putting hard numbers to those theories, constraining our models of Earth's total heat budget and its deep chemical composition. This data is even shedding light on the very origins of our world, offering clues about the distribution of elements during the violent process of planetary accretion billions of years ago. The ability to perform a planetary scan using ghost particles marks the birth of an entirely new field, neutrino geophysics. It transforms our understanding of the neutrino from a cosmic messenger into a terrestrial probe, turning the very ground we walk on into a transparent window, revealing the hidden fires that have shaped our world since its beginning. Deep within the pristine ice of Antarctica, a single ghost particle ended a cosmic silence that had lasted 6 decades. In December 2016, the IceCube Observatory registered an event of staggering violence, a collision with an energy of 6.3 peta-electronvolts. To grasp that scale, this one subatomic neutrino carried the kinetic energy of a tennis ball struck by a professional player, all packed into a particle a billion times smaller than a single atom. This was not just another high-energy event, it was a perfect match for a prophecy made long ago. In 1960, physicist Sheldon Glashow predicted a uniquely resonant interaction. He theorized that an electron antineutrino with just the right colossal energy could be absorbed by an ordinary electron. This direct collision would, for a fleeting instant, create a massive particle known as a W- boson, a carrier of the weak nuclear force. For over half a century, this Glashow resonance remained a beautiful piece of theoretical physics, a ghostly echo waiting for a source in the real cosmos. The universe simply never provided an antineutrino with the precise, tremendous energy required until that day in the deep ice. The detection was a textbook confirmation. The resulting particle shower, captured by IceCube's frozen array of sensors, perfectly matched the signature of a W boson's explosive decay. This single event, announced in 2021, did far more than validate a 60-year-old idea. It opened an entirely new window into the nature of cosmic accelerators. Before this, distinguishing an astrophysical neutrino from its antineutrino counterpart was nearly impossible. The Glashow resonance, however, is an exclusive club, one that only an electron antineutrino of a very specific energy can join. By identifying this one spectacular interaction, physicists could definitively label its source. It proved that the universe's most powerful cataclysms are actively producing these antineutrinos and hurling them across the void. This transforms our understanding of the cosmic engines themselves, offering a new diagnostic tool to probe the violent processes that give birth to such unimaginably energetic ghosts. One particle carrying a message from a distant cataclysm bridged a theoretical dream with experimental reality, reminding us that even the most fleeting of cosmic whispers can shout the deepest truths. The deep ice had finally spoken. In September of 2017, a single, spectacularly energetic neutrino struck the ice cube detector at the South Pole. This was not just another anonymous ghost, it carried an energy of nearly 300 tera-electronvolts, a clear signal that it was a messenger from an extreme cosmic event. For the first time ever, the observatory's real-time alert system was triggered, and an automated notice raced out across the globe to observatories watching every band of the electromagnetic spectrum. The coordinated hunt was on. Telescopes on mountaintops and in the vacuum of space immediately swiveled their gaze toward the patch of sky the neutrino had come from. What they found was a beacon of violence, a brilliant object known as a blazar, catalogued as TXS 0506+056. This blazar is not a star, but the heart of a distant galaxy, powered by a supermassive black hole weighing billions of times the mass of our Sun. This monstrous engine was not quietly consuming matter, it was actively firing a jet of plasma and radiation, and by a perfect cosmic alignment, that jet was aimed like a lighthouse beam directly at our solar system. The correlation was undeniable, the timing was precise, the location a perfect match. This was the long-sought smoking gun, the first time humanity could definitively point to a specific object in the cosmos and declare it a source of these high-energy cosmic neutrinos. This single event marked a paradigm shift in how we explore the universe. It was the true dawn of multi-messenger astronomy with neutrinos. We were no longer just looking at the universe, we were now listening to its ghostly whispers and immediately turning to see the light from the same cataclysm. By combining the direct, straight-line information carried by the neutrino with the rich data from telescopes, we could build a far more complete and powerful picture of the physics at work around these incredible black holes. It proved that the universe's most powerful particle accelerators are not just theoretical, they are real, they are active, and they are sending us messages written in the most elusive ink imaginable. This ghost has a weight, and we are finally learning to measure it. In a nondescript facility in Karlsruhe, Germany, an experiment of almost impossible precision is devoted to a single, monumental task, placing the neutrino on a cosmic scale. This is the Catron experiment, a technological titan designed to weigh the lightest known massive particle in the universe. Its method hinges on a quiet, natural process, the radioactive decay of tritium, a rare and heavy form of hydrogen. When a tritium nucleus decays, it transforms, spitting out an electron and, of course, an antineutrino. The total energy released in this transformation is fixed and known, a set amount shared between the two escaping particles. Most of the time, the electron carries away a large portion of this energy, leaving only a tiny slice for the ghostly neutrino. But in a tiny fraction of these decays, the scenario flips. The electron emerges with almost the maximum possible energy, leaving the neutrino with the barest minimum it can have, a sliver defined entirely by its own intrinsic mass. CATRIN is built to find these exceedingly rare events at the very endpoint of the energy spectrum. It is not trying to catch the neutrino itself, but to observe the faint shadow its mass casts. The experiment uses a colossal 70-foot-long stainless steel vacuum chamber, the largest of its kind in the world, to create a beam of tritium decay electrons. These electrons are then funneled into a giant electromagnetic spectrometer, a device that acts as a supremely sensitive energy filter, sorting the electrons with breathtaking accuracy. By counting how many electrons have energy just shy of the theoretical maximum, scientists can deduce the tiny amount of energy the neutrino must have carried away, and from that calculate its mass. This is not a simple measurement. It is like trying to detect the weight of a single snowflake by carefully measuring the change in weight of an entire mountain after a blizzard. The implications of this measurement ripple across all of physics. For cosmology, the neutrino's mass is a fundamental parameter that governs how the universe clumped together into the vast cosmic web of galaxies and clusters we see today. Even this phantom's minuscule weight, multiplied by the countless trillions that flood the cosmos, exerts a subtle gravitational pull, shaping the largest structures in existence. A precise mass measurement from CATRIN would act as a key input for our models of the universe's evolution, tightening our understanding of dark matter and dark energy. For particle physics, it is the final, crucial piece of the neutrino puzzle. Knowing the absolute mass scale, rather than just the differences between the flavors, is essential for theorists trying to build the next, deeper theory that lies beyond our current standard model. Every new, tighter limit from CATRIN, every step closer to weighing this cosmic whisper, forces us to confront the profound mystery of why it is so impossibly light, a question whose answer may lie in realms of physics we have not yet even begun to dream of. Two of the universe's greatest enigmas are engaged in a silent cosmic dance. We have the neutrino, a ghost we can barely detect, and dark matter, a phantom whose presence we can only infer through its immense gravitational pull. They are not the same entity, yet their stories are deeply intertwined in the architecture of the cosmos. The first connection lies in the ancient sea of relic neutrinos born from the Big Bang. This primordial background does, in fact, constitute a form of dark matter. These particles are massive, yet so light and fast that they stream through the universe at nearly the speed of light. This makes them what cosmologists call hot dark matter, but there is a problem. Their incredible velocity prevents them from clumping together effectively under gravity. If dark matter were primarily hot, its particles would have washed out the delicate seeds of galaxies, preventing them from ever forming. The fact that we see a richly structured universe filled with galaxies and vast clusters tells us that the dominant form of dark matter must be cold, moving slowly enough to collapse into the gravitational wells that sculpted the cosmos. The relic neutrinos are therefore a minor, hot component of the dark side, a whisper of substance against a far more dominant and mysterious cold shadow. This very distinction has led to a powerful synergy in our quest for answers. The monumental detectors built to catch neutrinos have a dual purpose. Their location, buried deep underground to shield them from cosmic rays, creates the perfect quiet environment to listen for something else entirely, hypothetical dark matter particles known as WIMP, or weakly interacting massive particles. Just like neutrinos, these theoretical particles would pass through most matter without a trace, only rarely bumping into an atomic nucleus. The same ultra-pure water, the same sensitive light sensors, and the same immense patience required to capture a neutrino's fleeting flash are precisely what is needed to have any hope of recording the gentle recoil of a nucleus struck by a WIMP. This is a beautiful convergence in science. The relentless technological drive to understand one invisible component of the universe, the neutrino, is simultaneously sharpening our tools and advancing the search for another. In the profound silence of a mine or under the polar ice, we are building instruments that listen for two different kinds of whispers at once, hoping that a signal from one great mystery will illuminate the path to solving the other. Yet the three known flavors of neutrino may not be the entire cast of this ghostly drama. Looming at the very edge of our understanding is a theoretical specter even more elusive than its known cousins, a particle called the sterile neutrino. This is a phantom of a different order entirely. While the electron, muon, and tau neutrinos are at least subject to the weak nuclear force, however feebly, a sterile neutrino would be entirely immune to it. It would feel only the pull of gravity, making it the ultimate ghost, a particle that could pass through a light year of lead as if it were not even there. Its existence would be inferred only through its subtle gravitational influence or through a bizarre quantum handshake with the ordinary neutrinos we can detect. The motivation for such a strange idea comes from a handful of stubborn experimental puzzles. Over the years, several independent experiments, particularly those studying neutrino beams from reactors and radioactive sources, have recorded a curious and persistent anomaly. They have detected slightly fewer neutrinos than expected at very short travel distances, a deficit that could be explained if some of the particles were oscillating into a fourth, sterile state and simply vanishing from the experiment's view. These anomalies are the faint, flickering clues that have kept this speculative possibility alive, a hint that our current map of the subatomic world might be missing an entire continent. If sterile neutrinos are real, their implications would be staggering. With a mass potentially far greater than the known neutrinos, they become a compelling candidate for a portion of the universe's missing dark matter, a heavy ghost that could silently shape the cosmos. Furthermore, their unique properties could provide the crucial, missing mechanism to explain the overwhelming dominance of matter over antimatter in the universe. Their presence would introduce new pathways for leptogenesis, the process by which neutrino interactions in the early universe could have tipped the scales in favor of our material existence. This speculative foray reminds us that the story of the neutrino is far from finished. Each time we believe we have pinned down its nature, it offers another, deeper layer of mystery. The search for sterile neutrinos is a testament to science's relentless drive to look beyond the established picture, to follow the faintest of anomalies into the darkness, ready for the next revolution. These ghostly particles have even escaped the confines of pure science to spark the imagination of storytellers. In fiction, the neutrino is often transformed from a subtle cosmic whisper into a tool of cinematic spectacle. The novel Solar imagines a plot centered on artificial photosynthesis, where the science of energy becomes a backdrop for human ambition. A far more dramatic misuse appears in the film 2012, where a fictionalized neutrino storm mutated by solar flares heats the Earth's core and triggers a global cataclysm. The real neutrino, of course, interacts so weakly with matter that this scenario is pure fantasy, a dramatic exaggeration that highlights our cultural fascination with invisible forces. These fictional portrayals, while scientifically inaccurate, serve an important purpose. They act as a gateway, translating an impossibly abstract concept into a tangible element of narrative drama. They make the invisible visible, if only through a distorted lens. The real challenge, then, falls to scientists and science communicators. Their work is to bridge this gap, to channel that initial spark of fictional wonder into a deeper appreciation for the true magic of reality. They use analogies, build stunning visualizations, and share the very human stories of discovery behind the detectors. The goal is not to dismiss the fictional tales, but to show that the genuine article is even more compelling. The real wonder lies not in a phantom that destroys worlds, but in one that can, without any interaction at all, reveal the hidden engines of stars and the radioactive heartbeat of our own planet. By turning this complex physics into a story of cosmic messengers and epic quests for knowledge, they transform public perception. A child who first hears of neutrinos through a sci-fi movie might later be the one who designs the next great underground observatory, inspired to uncover the real secrets these silent particles hold. This grand quest for cosmic ghosts is quietly reshaping the future of science itself. The dramatic story of the neutrino, a particle that requires instruments of mythic scale to detect, has become a powerful gateway for inspiring a new generation of physicists. Around the world, educational programs are turning this esoteric field into a hands-on adventure. High school students are no longer just reading about physics in textbooks. They are participating in initiatives that allow them to analyze real, raw data from detectors like IceCube, sifting through the same signals that might reveal a supernova or a distant blazar. This direct connection to the cutting edge transforms abstract concepts into a tangible hunt for discovery. For the wider public, the massive underground laboratories have become modern cathedrals of science, offering tours that descend deep beneath the earth. Visitors can stand in the cavernous halls of places like Surf in South Dakota, feeling the immense scale and hearing the hum of the machinery built to catch the universe's quietest whispers. This experience makes big science feel immediate and awe-inspiring, a human endeavor of epic proportions. The field's unique blend of cosmic scale and quantum weirdness captures the imagination in a way few other subjects can. It connects the infinitesimally small to the impossibly large, telling a story that is both intellectually profound and deeply human. Moreover, these projects demonstrate the essential, collaborative nature of modern research. A single experiment like Dune or Hyper-Kamiok and brings together thousands of scientists, engineers, and students from dozens of countries, all working toward a common goal that transcends borders. The quest to understand the ghost particle is about more than accumulating knowledge. It is about building a global community united by curiosity, dedicated to patiently and collectively uncovering the deepest secrets of the cosmos. Building a machine to see the unseeable demands an engineering philosophy that borders on the obsessive. The hunt for a single ghost particle begins with a war against every other particle in the universe. Cosmic rays from space constantly bombard our atmosphere, creating a cacophony of noise that would completely drown out the faint whisper of a neutrino. The only solution is to hide. These observatories are built deep underground, buried beneath a mountain of rock or sunk into the abyssal depths of ancient ice. This natural shield acts as a colossal filter, absorbing the relentless rain of distracting particles and leaving only the silent, penetrating neutrinos to reach the heart of the detector. But even then, the environment itself becomes the enemy. A single speck of dust, a minuscule trace of natural radioactivity in the very materials of the detector, can mimic the elusive signal scientists are desperately trying to find. This forces an almost unimaginable standard of purity. The water used in tanks like Super-Kamiok and is so clean it approaches the theoretical ideal of H2O, filtered and polished until it becomes a medium of unparalleled optical clarity. Any impurity would scatter the precious blue Cherenkov light, blurring the ghost's signature beyond recognition. For detectors using liquid argon, the challenge is even more extreme. The argon must be distilled to a level of purity never before achieved on an industrial scale, free from even a handful of rogue atoms that could trigger a false reading. Every component, every cable, every sensor that enters this sacred space must be meticulously cleaned and tested for radioactivity. because the universe's quietest conversation can only be heard in a room of absolute silence. Placing the ears to listen in this perfect silence is a logistical nightmare of epic proportions. Consider the deployment of IceCube's 5,000 optical sensors. Engineers did not simply lower them into pre-existing holes. They had to create the holes first, drilling 86 boreholes over a mile deep into the solid Antarctic ice sheet using a custom-built hot water drill TH, a T Chinese letter, a jet of scalding water at high pressure. Each hole, a perfect cylinder of liquid water in a world of solid ice, would remain open for only a matter of hours before the intense cold began to reclaim it. In that narrow window, a string of sensitive glass spheres, each one a highly sophisticated digital eye, was lowered into the abyss at a carefully controlled pace. The ice, under immense pressure from the weight above, slowly closed around them, freezing them in place for all eternity. A single miscalculation, a kinked cable or a frozen gear, and a multi-million-dollar sensor would be lost forever, entombed in the deep ice. This was not a one-time operation, but a multi-season campaign conducted in one of the most hostile environments on Earth, where human endurance was pushed to its absolute limit just to install the instruments designed to listen to the cosmos. The final detector is a masterpiece of stability and isolation. These are not machines that can be easily serviced. Once sealed, a detector like the upcoming Dune must operate flawlessly for decades, its internal environment held in a state of perfect equilibrium. The 70,000 tons of liquid argon must be maintained at a frigid -186°C, a monumental feat of cryogenics requiring a complex system of insulated tanks and cooling loops that must never fail. The electronics, designed to run for a generation, must be so reliable that their own inherent noise is lower than the signal they are built to detect. This grand-scale engineering, from the excavation of colossal caverns to the creation of ultra-stable, ultra-clean environments, underscores a profound truth about modern science. The theoretical flash of insight is only the beginning. Turning that insight into discovery requires a symphony of collaboration between physicists, engineers, drillers, and technicians, a global effort to build a cathedral whose only purpose is to capture a ghost. A neutrino message could travel directly from one side of the Earth to the other, unhindered by mountains, oceans, or the planet's molten core. This thought experiment pushes the ghost particle's unique property to its ultimate conclusion, a form of communication that treats the entire solid globe as a transparent medium. Imagine establishing a direct link between any 2 points on the planet without a single cable, satellite, or relay station in between. The signal would be perfectly secure, immune to interception or atmospheric interference, flying a perfectly straight line through the very ground we walk on. The applications could extend far beyond our world, into environments where conventional radio waves fail completely. A probe descending into the turbulent atmosphere of a gas giant, or flying through the intense radiation belts around a distant pulsar, could send its data out on a clean neutrino beam, a whisper that cuts straight through the cosmic static. Even the fiery plasma of a supernova, which blocks all light, would be transparent to these phantoms, allowing us to receive a clear transmission from the heart of a stellar explosion. The theoretical appeal is immense, a perfect cosmic telephone line, but the practical barriers are, for now, just as immense. To generate a neutrino beam intense enough to be detectable on the other side of the planet would require a particle accelerator of almost unimaginable power, one that would dwarf our largest scientific facilities and consume energy on the scale of a small nation. And the receiver on the other end would need to be a detector of staggering size, perhaps a cubic kilometer of ultra-pure water or liquid argon, just to decode a simple message from a single, powerful beam. The signal-to-noise ratio would be astronomically challenging, like trying to hear a single, specific whisper in a stadium where everyone is shouting at once. This is not a technology for tomorrow or even for the next century, yet this kind of speculative leap is a vital exercise. It was a deep, fundamental understanding of electromagnetism, once a mere scientific curiosity, that eventually gave us global radio, television, and the entire wireless world we live in today. By pushing the limits of our imagination with neutrinos, we are not designing a blueprint, but planting a flag at the farthest edge of possibility. It reminds us that the ultimate reward for unraveling the universe's most fundamental secrets is not just knowledge, but a potential for transformation that we can barely begin to conceive. This invisible river of cosmic messengers has never respected national borders, and neither does the science that seeks to understand it. The hunt for the neutrino is a fundamentally global endeavor, a testament to how the pursuit of a single, elusive truth can weave together the world's brightest minds. Consider the monumental Ice Cube Observatory at the South Pole, an international partnership involving over 300 scientists from nearly 60 institutions across a dozen countries. Its frozen components were designed in Germany, its sensitive optical modules assembled in the United States, and its data is analyzed by a distributed network of researchers from Sweden to South Korea. On the other side of the planet, the Super Kamiok and Detector in Japan, while hosted and led by Japanese institutions, thrives on vital contributions from teams in the United States, Poland, and Spain. This collaborative spirit reaches its zenith with the upcoming Deep Underground Neutrino Experiment, DUNE. It unites more than 1,000 scientists from over 200 institutions across more than 30 countries, from Brazil to India, from Switzerland to the United Kingdom. These are not merely lists of participants, they represent a new model for humanity's grandest projects. No single nation possesses all the required expertise, financial resources, or engineering capacity to build and operate these cathedrals of science alone. They demand a pooling of global intellect, a sharing of technological marvels, and an open exchange of data on a scale never before seen in fundamental physics. This creates a powerful dynamic where a breakthrough in cryogenics from Italy can directly enable a discovery in a South Dakota mine, and where a theoretical insight from a researcher in Russia can reshape the analysis of data collected under the Japanese Alps. In an age often defined by division, these collaborations stand as beacons of peaceful, purposeful unity. The shared goal is not territorial or economic advantage, but a common thirst to read the universe's most hidden messages. This spirit transforms neutrino physics into something more than a branch of science. It becomes a profound human enterprise, a silent agreement that the deepest cosmic secrets belong to no one nation, but are a legacy for all of humanity to uncover together. Such immense projects, funded by public investment, inevitably carry a profound ethical weight. When a society allocates billions toward understanding cosmic ghosts, it raises a fundamental question about the balance between the quest for pure knowledge and the pressing needs of the here and now. Is it justifiable to build a cathedral of science deep underground when communities above may face challenges with infrastructure, healthcare, or education? This is not a question with a simple answer, but a necessary dialogue at the heart of modern research. Proponents argue that the pursuit of fundamental understanding is a core part of our humanity, a long-term investment that has historically yielded unforeseen and transformative benefits. The very internet you use to watch this video emerged from the need to share data between physicists at CERN. The development of the World Wide Web was not the goal of their research into particles, but a revolutionary byproduct. Similarly, the relentless drive to create ever more sensitive sensors for neutrino detection pushes the boundaries of materials science, computing, and data analysis, innovations that inevitably ripple out into the broader economy and society. The argument is that by looking to the farthest horizons of knowledge, we ultimately develop the tools to better navigate our own world. Yet this does not absolve scientists and funding bodies of their responsibility. There is a growing recognition that the teams behind these monumental experiments must actively and clearly communicate their work's value and progress to the public and the policymakers who represent them. This goes beyond press releases about a new discovery. It means translating complex goals into a compelling story of human curiosity, explaining not just what they are doing, but why it matters to our shared understanding of the universe and our place within it. This transparency builds the public trust that is the true foundation for such ambitious, long-term endeavors. Alongside this is a critical focus on environmental stewardship. The construction of a facility like the Deep Underground Neutrino experiment involves moving massive amounts of rock and consuming significant energy. In response, these projects are now designed with mitigation as a core principle. At the Sanford Underground Research Facility, the former Homestake Mine, careful water management and rock recycling programs minimize the footprint. The laboratories are often designed for extreme energy efficiency, with plans to use waste heat from equipment to warm buildings on the surface, turning a logistical challenge into a community benefit. This mindful approach extends to the very purpose of the science itself. By probing the nature of matter and the origins of the cosmos, this research addresses the most fundamental questions humanity can ask. Who are we? Where did we come from? What is the universe made of? The answers to these questions, however abstract they may seem, form the bedrock of our cultural and intellectual heritage. They inspire generations of students to pursue careers in science and technology, building a skilled workforce for the future. They provide a shining example of what humanity can achieve through global cooperation, a shared project that transcends conflict and division. The ethical path forward, therefore, is not to halt the quest for knowledge, but to pursue it with a renewed commitment to responsibility, transparency, and a humble awareness that our greatest explorations of the cosmos are ultimately a reflection of our values here on Earth. The neutrino dissolves the solid world around us into a phantom architecture. Every desk, every mountain, your own hand, is less a permanent object and more a temporary constellation of energy, perpetually transparent to the most abundant matter particles in the cosmos. This forces a profound shift in how we perceive reality. We are taught to trust our senses, to believe in the tangible solidity of things. Yet the universe is clearly built from a foundation that is utterly invisible to our biological perception, a hidden framework where the rules are written in the language of quantum mechanics. The neutrino is the ultimate teacher of this lesson. Its very nature is a continuous performance of quantum strangeness on a grand scale. Consider the chameleon-like oscillation between flavors. An electron neutrino born in the Sun does not simply travel to Earth as a single, defined entity. According to quantum law, it exists in a blurred state of superposition, a simultaneous mixture of all three possible identities: electron, muon, and tau, until the moment it is finally detected and forced to choose one. This is not a mere technical detail. It is a fundamental characteristic of reality at its smallest scales, and the neutrino performs this quantum ballet across cosmic distances, weaving through planets and stars without a single collision. It demonstrates that the certainty we crave in our daily lives is an illusion, a convenient approximation that breaks down completely in the subatomic realm. The solid, predictable universe of our senses gives way to a realm of probability and potentiality, where a particle can be in multiple places or hold multiple identities at once. This hidden activity challenges the very notion of what is real. Is reality only what we can directly see and touch, or is it the vast, invisible dance of particles and fields that constructs the stage upon which our visible world is set? The neutrino argues powerfully for the latter. It compels us to accept that the true substance of the cosmos is this intricate, mostly unseen interplay of forces and phantoms. Our monumental efforts to build detectors are not just scientific pursuits, they are acts of philosophical awakening. Each blue flash of Cherenkov radiation in the deep ice is more than data. It is a momentary glimpse behind the curtain, a brief illumination of the wondrous and bizarre quantum engine that powers everything. Embracing this hidden reality does not diminish our world, but infinitely enriches it, revealing a cosmos of far greater complexity and majesty than our limited senses could ever perceive on their own. From a desperate theoretical ghost to a cosmic messenger of immense power, the story of the neutrino is one of science's greatest journeys. This phantom, born to balance an equation, has become our most direct link to the hidden engines of the universe. It whispers the secrets of stellar furnaces, screams the final moments of dying stars, and even carries the faint radioactive heartbeat of our own planet. We have learned that these particles are not simple but chameleons, constantly shifting their identity in a quantum dance that proved they have mass and shattered our existing model of physics. They flow through us in an endless flood, a direct connection to the Big Bang itself, yet their profound weakness is their greatest strength, allowing them to travel billions of light years unimpeded, carrying pure, unaltered stories from the cosmos's most violent events. The physicist John Archibald Wheeler once offered a profound reflection. He said, "We live on an island surrounded by a sea of ignorance. As our island of knowledge grows, so does the shore of our ignorance." Our exploration of the neutrino has dramatically expanded our island, revealing new continents of understanding. Yet with every answered question, a new and more thrilling coastline has appeared, a horizon filled with deeper mysteries about their mass, their role in creation, and their connection to the dark universe. The endless flood of these phantoms represents both the ground we have won and the vast, exciting unknown that still lies ahead, a silent, perpetual invitation to continue the greatest voyage of all.